let's see. So we need our lab manuals. Of course, we need our log books. And so I've got mine over here ready to go. At the moment, I'm going to be using my tablet to write notes on the pages. Excuse me. But of course, you guys remember date, time, initials. And for today, always want to get date, time, initials. Okay, so we still haven't added anybody in the last couple minutes. All right, so there's someone. Okay, I mean, we can afford to wait, I think, for another minute or so because we're not going to take the whole period, I don't think. Everybody should open up a spreadsheet, please. Most likely it's going to be Excel. It might be numbers, I suppose. I forget what the Macintosh is. Okay. And, whoops. We'll go over this. So now we've made it to, well, not quite, almost 5 minutes. And the recorder is on. Okay. So, all right, well, let's take a look here. So we had some terms to define and statistical and systematic errors. So, for example, they showed what's called a counting experiment. And so, in a counting experiment, we can say that the error is expressed as the square root of whatever we counted. And so obviously, the more we count, oh, maybe not obviously, let's be careful, sorry. So maybe I should get myself a notepad going on here. Okay. All right, we don't need this. Okay, so in a counting experiment, so if we say that we measure, so we measure some number to be n, and so the error on that number is just simply square root of n. So if I measure something to be 10, square root of 10 is like 3.1. So now, if I measure something to be 100, that becomes plus minus 10. Now you'd say, well, heck, seems like I don't want to keep measuring more stuff, right? But you have to be careful. You have to do, this is what's called the absolute error. And usually anything that's expressed plus minus is the absolute error. And we're going to look at this next week. It's usually used this low uppercase delta. And then there's the fractional error. And that's expressed with the lowercase delta. We'll get into this again next week. So what happens is then that's the fractional error is the plus minus n over n. And so, or in our case, then for a counting experiment is square root of n over n. And I mean, we can make a graph, but the quickest thing to notice is you have 3.1 over 10 equals 0.31, whereas 10 over 100 is 0.1. So you see how, as you count more and more, your fractional error goes down. So it's always good to count longer if you can. Okay. I want layout. And let's see, save as, computer. Let's see, I want 2100 labs. I don't see it, so I'm just gonna have to find it. I'm not, oh, hey. Yeah, I'm going slowly. And I'm right, yeah, you should have your logbooks open. Thanks, guys, that's right. Date, time, initials. You should have something written in there or pasted in there. Lab sections, 2100, statistical analysis of data. So this is going to be 2110 notes. So I'll publish this later on. Okay, so now when I save it, it'll autosave for us. So in a statistical error, we're going to learn about that. Today, we're examining a different type. We're not doing a counting experiment. We're actually measuring something, but we're measuring it n number of times. So a statistical error is something related to the number of times you measure something. And we are not going to deal with this too much in 2100, but a little bit, enough that you're going to see later on why we do certain things. Okay, and then a systematic error. Okay, systematic error. Now I expect that you handed in notebooks last night, so I'm going to double check that you made some attempt at this, but you should definitely, and it's so far it's pretty simple, but you should double check that what you wrote down matches what I wrote down, and maybe you have more. A systematic error is something about your instruments or your technique. So let's say you have a ruler, a plastic ruler, maybe one could imagine. And it got really hot and it shrunk. So it's not going to give you the right measurement anymore. So that's an example of a systematic error. Now, in our case, we took our ruler and we moved it around every time. And in fact, good practice says that we should always try to line up the zero. We should always try to line up the zero on one end of the object that we're trying to measure, which we purposely did not do. Okay. So these are pretty simple, right? So what's next? Accuracy and precision. So these are words that people use a lot, and we need to learn how to be careful when we use these words. So accuracy means how close to real value. And so your experience with this, when you do percent errors, you do some like measured minus accepted, right? So when you do an analysis in high school chemistry, you're actually doing an assessment of what your accuracy is. But that's compared to a standard. In general, we don't know. We don't know actual value. And this is why scientists and engineers, to some degree, spend a lot of time on error analysis and describing when they do it. Why I'm asking you, when you do these things, to write detailed notes about what you did. Because when you get to the point where you're doing a real experiment, those notes are incredibly valuable and necessary. So you can chase down systematic errors, for example, and you can convince people that you've made an accurate measurement, that they should believe you. Now, precision there's a couple ways of stating this. This is like the number of sig figs. So if I say something is 2.1, there's sort of implied that this digit here, it's like plus or minus 0.05. But if I put 2.123, and let's say this is centimeters, well, let's make it meters easier. So you're telling people that you are good to like a few centimeters, whereas here you're down to tenths of a millimeter. Now, of course, you're really supposed to put plus minus. So precision has to do with the size of your error. And you have to be in the real world. When you publish a paper and people look at your paper and they look at your result, that's right, they're happy. But the most important thing is going to be your error, but what they call the error budget. Excuse me. Because if you want to claim let's say that somebody in the past, group A, has said that they've measured some quantity that's 5.15 plus or minus 0. Oops. Here we go. Black plus or minus 0.05. And then you come along and say, well, I think it's 5.5. But then you say, well, plus or minus 0.4. Then, and you're group B, nobody cares. Because you haven't demonstrated anything. All you said is that Group A is probably right, and they'll thank you for it, but they still get all the credit. So this week and next week, we're studying this. Excuse me, the precision and the error accuracy. Well, that's sort of and ironically, though, in some sense, though, this does have to do with accepted values, because I know that many of you noticed, several of you wrote to me to say that you got the same measurement for the length every time, and that's when I posted an announcement with a video for you and asked you to cheat a little bit. Well, yeah, you don't have to. It's up to you. You could submit it like a totality. Basically, for today, I expect you at least submit whatever is new from today. Yep, that's right. Okay. So let's take a look at these slides that I got from the University of Rochester. So you're counting the number of blades of grass. And right, I showed you about how as you count more and more, you're getting, and so what you're trying to do is like count the number of blades of grass per square meter. So you could count 1 square meter, you could count 10 square meters, and your error is going to go down. Yeah, a systematic error might be that we have a bad tape measure. Yeah, how good is our ruler? Was the piece of lawn we picked, was it flat? You know, if it was curved, if it was on a hillside, we could get errors. So all these things have to be taken into account, and that's why when you're taking data, you have to write things like that down. I'll tell you a true story. I was working on an experiment at Brookhaven National Lab, and we had these detectors, and essentially the detector had, so you had the particles would collide here, protons, and then stuff would fly out, and inside this detector was a bunch of wires in a big array. And so the particle going through would leave a track of electrons, and the wires would pick it up, and we'd know where the particle was. And then also you could figure out this curvature, for example, and without going into detail, that's a way of figuring out how fast the particle is going. So some people were doing data analysis months later, and they noticed that there was a problem with the data. And so somebody suggested that they go back and find a weather report from that day. And it's like, what? So there's a gas inside of here. And part of the gas was methane, which is flammable. And so the safety people would not allow us to keep this sealed. We were not allowed to seal this detector. We had to provide a hose, and we had ways of keeping air out. Like, oh yeah, I know a very simple way to do this is that you take the hose and and then you run it into a pot full of oil, for example, and then the outside air can't get in. But the point is that the pressure inside the detector was pressure detector was equal to the pressure of the atmosphere. And sure enough, on that particular day, a big thunderstorm came through and the barometric pressure crashed. So people used to laugh at me because whenever I would sit down a shift to take data, I would always write down my date time initials. And then my first entry would be that, I'd say this is Harry Tiemann. Today is this day. At the moment, the weather outside is sunny and clear, or the weather outside is raining. I would quote the temperature, and I remember people laughing at me by writing that stuff down like that. But you know what? It came, luckily too. They looked it up in the newspaper. But then at that point, they changed the data computers, so the data computers recorded the air pressure and the temperature outside as well, and that was put into the database. Not because of me, but just that because of that incident. So it's very important to write everything down. In Physics 2100, of course, the weather isn't the end of the world, but I'm just giving you a taste of it. Okay, what's next? What about another thing is that we want to determine how many blades of grass in a square meter, and we all know that different areas of the lawn have some are really dense and green, and some are kind of brown. So these are all kinds of ideas to work on the systematic errors. Yeah, right. Global warming, these errors, and like in the beginning, it talked about a political survey. And so, yes, you always need an estimate of an error, a value, error, and units. And then let's see. Oh, right. And you guys won't get into it, but you quote a statistical and systematic error depending upon what kind of experiment you're doing. Closeness to the truth, right? And then precision measure of reproducibility. Interesting. I see what it means. That, right, you're telling people if you do the experiment your way, that you're always going to get 10 plus minus 2 plus minus 3 every time. That could, if you do it our way. So you're telling people how careful you were. Another way to state what I wrote earlier. Okay, and then this is the like you're throwing darts, right? This is the classic dartboard. So if the darts are very close together, you have a very precise throw, right? There's not much variation, just like your plus minus is small. However, if they're all stuck in the wall, it's not very accurate. And so you see the various conditions here. So, of course, they're close together, they're in the middle of the target. But I remind you once again, for the most part, we cannot see the target. We don't know where the target actually is.